Good afternoon, ladies and gentlemen. My name is Philip Bell. I'm the Chief Commercial Officer of iThera Medical, and I would like to welcome you to this exclusive webcast on using multispectral optoacoustic tomography for cancer applications. We will have about 30 to 45 minutes of presentation, and then we'll open it up for questions. You can type your questions at any time in the question box on the webinar status bar. We will try to cover as many of them as we can during the Q&A at the end. In addition, this presentation will be recorded, and you will all receive a link to the recording in the follow-up email in the next few days. And now let me hand it over to my colleague, Dr. Neal Burton, who will lead you through the presentation.
Thank you, Philip. As you said, my name is Neal Burton. I'm an application scientist working for iThera Medical, and today I'll talk about multispectral optoacoustic tomography, which we abbreviate to MSOT, and talk about applications in cancer research. I'll first start out by talking a bit about how optoacoustic tomography works. So we use a tunable laser that's tunable in 1 nanometer steps in the range of 680 to 980 nanometers to illuminate a molecule of interest. The multiple lines that are shown here in this cartoon indicate the individual wavelengths that we would use to illuminate our sample. The energy from the photons is then absorbed by the molecule. Electrons within this molecule then become excited, leaving the ground state and entering the excited state. When these electrons return to the ground state, as it's well known, you can either have a fluorescence, or more commonly, the molecule can give off just a small amount of heat, which creates a thermoelastic expansion surrounding the molecule and makes a pressure wave that can be detected as a sound. Our approach to imaging is tomographic, meaning that we place an array of detectors around the molecule of interest. And within this array of detectors, we can have up to 256 individual detectors, each detector being a 5 megahertz ultrasound transducer that allows us to have an in-plane resolution of 150 microns. For each of the individual wavelengths that we use to illuminate our sample, we reconstruct an individual grayscale image that reflects the total optoacoustic amplitude at that particular wavelength. We can then use spectral and mixing algorithms on this stack of images to look at the change in optoacoustic amplitude on a pixel-by-pixel basis over the wavelengths, and then determine the distribution of a molecule of interest. This is shown on the right, where we're using one of the individual grayscale images as a background image for an anatomical reference, and we overlay on top of that in pseudocolor an image that reflects the distribution of an injected agent, in this case ICG injected into an animal that was bearing a subcutaneous 4T1 tumor. So the advantage to MSOT then is that we can acquire both molecular and anatomical information simultaneously. The image that we show in the lower panel shows a cross-section of a mouse, of a mouse leg that was injected with a point source with Alexaflor 750. So as you can see in the MSOT image, we can see both the anatomy of the leg, including the tibia, fibia, and also an artery within the leg, but we can also see in the jet-colored scale the Alexaflor that was injected into the animal. With ultrasound, we can see some structural information, but we don't see the molecular agent. With CT, of course, we can see the bones, but we cannot see the molecular agent. If you look at epifluorescence, in this case with sectioning and looking at the fluorescence signal in cross-section, we can of course see the Alexaflor 750, but we lack the structural information within the sample. The benefit then of MSOTs is that we can acquire a 10 to 100 times resolution as compared to PET or optical imaging. With PET, you typically have an in-plane resolution of 1 to 2 millimeters. With optical imaging, because photons can be scattered by tissue on their way outside of the tissue, we can have a destruction of resolution as a function of depth. Because we illuminate multispectrally, we can acquire molecular specificity, and we acquire our data in real time at 10 hertz, so we can image events as they occur. Because we do not use ionizing radiation, the modality is seen as both safe and cost efficient. As I said, the laser that we use operates in the range of 680 to 980 nanometers, where we can tune the laser in 1 nanometer steps. That allows us to see various probes of interest. It's important that the probe that we're imaging has a characteristic absorbance in the near infrared within this region, and that's an important point because we image the absorption, not the emission of particular probes of interest. By being able to look at the near-infrared window, the types of probes that are suitable for MSOT imaging include commercially available organic dyes, such as Psi 5.5, IR dye, ICG, Alexafluor 750, and similar cyanide dyes. We can also see bio-inorganic nanoparticles, such as gold nanorods, carbon nanotubes, or quantum dots, so long as their absorption profiles have been tuned to absorb in the near-infrared. We can also see fluorescent proteins, such as IRFP, a recently characterized fluorescent protein that has a characteristic absorbance at 692 nanometers. It has a low quantum yield of 6%, so it is not yet widely used protein within the fluorescent community, but because we image the absorption and emission of heat, a low quantum yield actually works in our favor. So IRFP is something that works very well as a genetic reporter in MSOT. The information that's acquired, therefore, with MSOT is anatomical, based on the optical absorption of tissue. In this particular image, this color scale indicates in white pixels areas of a mouse that have high signal from blood. So we see in the center of this mouse the vena cava. We also see throughout the mouse other smaller vasculature throughout the mouse. So this defines the anatomical information, but we can also acquire structural information from other intrinsic absorbers in the mouse, such as melanin. We can also acquire functional information by injecting non-targeted agents and looking at perfusion, or by looking at oxygenation directly, since we can see oxygenated and deoxygenated hemoglobin due to its characteristic absorption in the near-infrared. We can also see molecular probes by using multiple wavelengths, whether they're targeted or non-targeted, and we can also see fluorescent proteins, as previously discussed. And because we acquire data at 10 hertz, we can establish pharmacokinetic parameters for injected agents and look at biodistribution of injected agents throughout an animal. The following animation will show how an MSOT experiment works. So the device itself has about a 1 square meter footprint in the lab. It's on wheels so that it's easily movable. As I start this video, I'll show how the imaging works. As I stop this video, you can see that the mouse goes into an animal holder where it receives gas isoflurane anesthesia so that the animal is asleep while imaging. If I continue the video, you'll see that I put the animal into an imaging vessel, to an imaging tank. Pardon me, I inadvertently advanced the video. So now if I pause the video while the animal is inside the system, then you can have a look at the 270-degree transducer array that detects the ultrasound signals and also is a source of the near-infrared lights that we use to illuminate the mouse. The mouse is then translated through the imaging plane where we can acquire sequential cross-sectional images where we illuminate with light and detect outgoing sounds. We can then translate the animal through the imaging plane so that we can acquire successive two-dimensional cross-sectional images, and if we like, as I'll show in this presentation, we can render three-dimensional volumes offline. The topic of today's webinar is imaging cancer, and as a backdrop for this discussion, I'd like to show the hallmarks of cancer as defined by Hanahan and Weinberg, originally in the 2000 publication in Cell and updated in 2011, where they discussed 8 different hallmarks of cancer and 2 enabling characteristics, such as tumor-promoting inflammation and genome instability and mutation. So this cartoon shows these 10 different parameters of cancer that are of general interest to the cancer community. Each one of these parameters is described in text outside of this circle. And the ones that are labeled in green are the hallmarks that have been shown to be imaged either directly in optoacoustics or in optical imaging, which also applies to optoacoustics. The particular items that are in bold, such as sustaining proliferative signaling, tumor-promoting inflammation, imaging metastasis, and resisting cell death, are specific applications that I'll discuss in the following slides. We'll return to this paradigm at the end of the presentation to see what optoacoustics can image with respect to the hallmarks of cancer. So first, we'll talk about visualizing vessels and oxygenation status in an attempt to characterize angiogenesis within a growing tumor. So what we've done in this case is illuminate an animal multispectrally that was bearing a 786O renal carcinoma cell line that was implanted into the leg region of this mouse. This study was done with one of our customers in Tokyo. And then what we did was separate out the multispectral signals into oxygenated hemoglobin, which you see on the left here in red, or deoxygenated hemoglobin shown on the right. What we see is that oxygenation alone is not enough to characterize the tumor boundaries, but in the area of the image that was known by the investigator to be part of the tumor, we can see that the tissue is very heterogeneous with respect to oxygenated and deoxygenated hemoglobin. The oxygenated hemoglobin signals do a very good job of showing us the vascularity of the tumor, while the deoxygenated channel in MSOT shows us a hypoxic area within the tumor. The images here on the left are maximum intensity projections that reflect a two-dimensional representation of multiple cross-sections that were acquired within the animal's leg in this case. But we can also render those two-dimensional cross-sections as a 3D projection shown here, where we can really see the three-dimensional relationship of these structures to each other. Gives you a better idea about the shape and size of the tumor and the areas of hypoxia. But what can sometimes also be useful is to not just look at the oxygenated and deoxygenated signals separately, but rather combine them to get a metric of oxygen saturation, where we plot on a single color scale oxygenated hemoglobin divided by the total hemoglobin signals, and plot that on the color scale shown at right, so that we can really much more easily visualize the hypoxic area within this tumor. This can be shown with the saturation information alone, or overlaid onto one of the single wavelength grayscale images for an anatomical reference. So this allows us to look at both the vascularity and the oxygenation status of a growing tumor. Another collaborator in China also wanted to look at the biodistribution of an injected optical agent in a tumor model. So in this case, the investigator wanted to compare traditional optical imaging with planar fluorescence, shown at the top, with performance by MSOT over the same time period. And what we see is that the agent that was injected, which was non-targeted and should accumulate in the tumor solely by the enhanced permeability and retention paradigm, we see over the course of 48 or 72 hours that planar fluorescence imaging shows that this compound did in fact accumulate in the tumor. We see the same thing by MSOT, only in this case we get a cross-sectional image rather than a planar fluorescence image. We could also quantify such signals over time and also co-localize that information from an injected molecular agent or non-targeted agent with hypoxia information. And in this case, what we see is that the tumor that was growing this animal had a hypoxic core, and the molecular probe that was accumulating within the tumor was accumulating in the hypoxic part of this tumor. We can image the animal over time and see an increase in signal over the course of 48 hours. We can also look at the accumulation of a probe in a tumor three-dimensionally, as we've shown already in 3D projections, or by looking at this in orthogonal views. And what we see in this case is that by looking at such projections, we can really discriminate a part of the tumor from neighboring regions, which in a fluorescence setting might look like they're coming from the same area. We've also looked at the ability to use this technology in the context of dynamic contrast enhancement, which is common in MRI, but can also be used in MSOT, where again, a non-targeted agent can be injected into an animal bearing a tumor. We can then draw a region of interest around the tumor and plot the change in signal over time, so that over this 30-minute period, we can see a rapid increase in probe in the tumor, and we can see this decrease over time. We can then model this change in concentration pharmacokinetically and establish rates for K in and K out. This was done in an animal that was bearing a 4T1 tumor, and in this case, lysosomal ICG was injected into the mouse so that we could have an extended half-life, as the half-life of ICG is about 3 minutes, which is a bit too fast to try to do such an experiment. But in this case, what we could do is after we've modeled the change in signal in the tumor over time, we can now apply such an analysis on a pixel-by-pixel basis within the images. So that if we restrict this parametric map to just the tumor region itself, so the pseudo-color applies only to the tumor region, not to the grayscale part of the animal as well, we can see the maximum signal that was reached over the 30-minute period of this experiment plotted on this color scale, with black colors indicating a low level of signal over the course of the experiment, and yellow and white colors indicating a high level of signal over the course of the experiment. This is another way that MSOT can be used to document the tumor, the heterogeneity of a tumor. This would suggest that these structures on the outside of the tumor are blood vessels that are supplying blood to the tumor, and that on the inside of the tumor there's really a paucity of perfusion. We can also look at the time it took to reach this maximum concentration and plot that on a separate color scale, shown here in the middle, with blue colors indicating a relatively quick time to reach the maximum concentration, again, the blood vessels that are feeding the tumor, and red colors indicating a long time with which it took to reach the maximum concentration. This is another way to look at tumor heterogeneity that would not be available by planar fluorescence imaging, but is done by MRI. But what you don't get in MRI with every routine that's run is simultaneous information with respect to oxygenation. And in this case, it's really complementary to what we can see with respect to dynamic contrast enhancement, because we can see a high level of oxygenation in these structures that were seemingly having a high concentration of probe early in the experiment, and when we look at the oxygenation, then it's clear that these are most likely vessels. When we look at the deoxygenated colors, this is shown in blue, then we can see the interior of this tumor is truly hypoxic, which puts the parametric maps that we saw in the first two cases into perspective. There's poor perfusion because the tumor is hypoxic, and these ideas go hand in hand. But the advantage with MSOT is that we can see these parameters simultaneously in a single mouse in a single experiment. We've also looked at the ability to use molecular probes to image apoptosis within MSOT. We used a molecular probe that would target caspases, and we injected this into an animal. We then can look either at a single static image, a single wavelength image to show the anatomy, the boundaries of the mouse, and so on. Because we illuminated multispectrally, we get information with regard to oxygenation, so we can see it's also a heterogeneous tumor. But what we see in the time-lapse video on the right is over the course of 60 minutes, we can see the accumulation of this molecular probe in the tumor. But what we see, interestingly, is that the accumulation of this apoptosis probe was co-localizing with the part of this tumor that was shown to be hypoxic by our oxygenation measurements. At the end of this period of time-lapse video generation, by imaging a single cross-section of the mouse, we could then image a volume of the mouse. This is shown on the next slide, where then we image the entire tumor, shown in the middle. What we show here is actually two different probes that were injected simultaneously. The green probe is the one I showed on the previous slide, which showed an accumulation over the course of the experiment, and was the molecular probe that was specific for caspases. The blue pixels in this 3D rendering represent a non-targeted agent that was injected simultaneously. It had a different absorption spectrum and was used as an indicator of perfusion to really show the difference in this particular experiment between simple perfusion through a tumor and a molecular event that was happening in that tumor, shown here with the green pixels. We could then quantify the signals that were within the tumor over the experiment, and we see that while the apoptosis probe was always increasing over the 60 minutes of this experiment, the control probe, shown in blue, reached very high levels quickly and then was quickly eliminated as well over the course of the 60 minutes. We validated this experiment ex vivo, where we sectioned the animal and as well imaged the sectioned animal multispectrally to look at the same signals ex vivo that we looked at in vivo. So we see that the apoptosis probe indeed accumulated within the tumor, while the control probe was simply perfusing other parts of the mouse, and then there were some regions that showed both probes. To validate that this particular probe was specific for apoptosis, we also treated the animal with doxorubicin following an initial imaging session to show that after doxorubicin treatment and apoptosis induction, we indeed imaged a higher level of apoptosis within the tumor. The half-life of this apoptosis probe was sufficiently short that we could do imaging from one day to the next. In this particular experiment, moving on, we look at the ability of using molecular probes with MSOT to look at endothelium receptor levels within a tumor. Endothelium receptor levels should be increased in the context of hypoxia. And what we see when we look at these three-dimensional representations is that there are clearly two different areas of accumulation within the mouse. One within the tumor, shown at the bottom, and then another signal that is shown adjacent to the tumor, which is known to be the spleen. In a planar fluorescence setting, one might not be able to discriminate the signals from each area since they're so close to each other, but by being able to image cross-sectionally and three-dimensionally due to our tomographic approach, we can separate out these two signals. One of our customers in the United States, Dr. Lacey McNally at the University of Louisville, which I show here at the bottom, she recently used this technology to support a paper that was recently accepted for publication in the journal Surgery. And in this paper, she used a human pancreas cell line to generate an orthotopic pancreas tumor model in mice, where she injected these tumor cells directly into the pancreas. She then imaged by MSOT using a syndikin-1 receptor ligand. Syndikin-1 is a transmembrane receptor that will be cleaved, and it then acts as a growth factor, which can promote metastasis and cellular proliferation. So by using this molecular probe, she can image, in this case, different cross-sections 6 hours after injection and show that there was a specific accumulation in the pancreas. When she would draw different regions of interest, either around the pancreas tumor or different parts of the animal, such as the liver or spleen, she could see that she had a specific signal. If we look at the optoacoustic signal versus position, she had a high signal from the probe within the tumor, but in other areas of the mouse, there was no increased signal from the injected agent. These are cross-sectional views that we can look at, but we can also image the mouse in multiple cross-sections and render a three-dimensional volume, as she did in this case. And in this case, the orthogonal views show us the shape and size of the tumor volumetrically. She then validated this ex vivo by looking at the fluorescence signal from planar fluorescence and saw that the signals from the tumor from the labeled probe were really specific for the pancreas and were not present in either the spleen or the liver, which was very consistent with the in vivo imaging that was performed. We've also looked at the ability of using MSOT to image the fate of injected cells that can be labeled and injected into tumor-bearing animals. In this case, macrophages were grown in a petri dish and labeled with a lipophilic near-infrared dye that absorbed at 800 nanometers. These macrophages were then injected into a mouse bearing a 4T1 tumor, and they were shown to home back to the tumor as shown here on the jet color scale. This accumulation was shown to be progressive over time, showing the highest degree of accumulation after 24 hours. So it's possible to use MSOTs to do cell tracking in vivo. We've also looked at the ability to use IRFP, again a fluorescent protein that absorbs at 692 nanometers, as a genetic reporter in MSOT. And then we compared its performance in MSOT to its performance in other imaging modalities that can pick up these signals, namely fluorescence molecular tomography combined with CT or a planar fluorescence approach. And what we saw was that in this model of glioblastoma, that through an intact skin and skull, we could image the size, shape, and location of this tumor with high specificity, as shown by the ex vivo validation, that could really not be achieved by the other imaging modalities. The reason that the signal is so specific in MSOT is that we're imaging ultrasound waves that are generated by the absorption of light from the reporter molecule. These sound waves are scattered by 3 orders of magnitude less than photons in tissue. That's why we can detect very small signals within MSOT that cannot be achieved in traditional optical imaging. In addition to using IRFP as a genetic reporter, one can also use melanin as a genetic reporter, as it has a very high absorbance in the near infrared. So a collaborator here in Munich, near Munich at the University of Würzburg here in Germany, looked at the ability to use a tyrosinase promoter to generate melanin within cells and use that as an optoacoustic reporter. They tested multiple different constructs and saw that one particular construct gave the highest signal after transfection, so they used this going forward with in vivo studies. It's important to note that their mode of delivery of these genetic constructs to the cells was with a vaccinia virus, which should show a specific uptake in tumor cells as opposed to non-proliferating cells. They then looked at the ability of this vaccinia virus to label a primary tumor. In this case, the primary tumor is shown here. And what we see is that in 5 different spots of this tumor, we see black signals from the growing melanin. We can then look at the different wavelengths that we can image in MSOT. And even in the single wavelengths, we can see the hyperintensities from the melanin signals. We can also then divide these multiple wavelengths into molecular signals to differentiate hemoglobin from deoxyhemoglobin from oxyhemoglobin to generate a specific signal for melanin. And when we do that, we can see a high degree of specificity accounting for differences in the way the animal is positioned from ex vivo sectioning to in vivo imaging. But we see a high degree of specificity within the primary tumor with respect to the melanin signal. That's important for imaging the primary tumor, but what the investigators were also interested in was imaging metastases in this model, shown on the next slide. In this case, they injected the vaccinia virus into an animal bearing this primary tumor, and what they saw in this case is that they had hyperintensities for the melanin signal in areas that were known to be the lymph nodes. This was validated ex vivo, where the lymph nodes were visually quite dark. So in this way, vaccinia virus containing a melanin construct can be used not only to image the primary tumor, but also micrometastases throughout the mouse. So going back to the hallmarks of cancer, what we've seen in the past slides is that we could evaluate receptor status by using, for example, a molecular probe that targets an extracellular receptor. In this case, we showed SYNDICAN1 expression level could be used to show a primary pancreatic tumor. We also saw that we could do cell tracking and image the fate of injected cells by labeling macrophages with an organic dye and then imaging the mouse in vivo over time. We also looked at the ability to image micrometastases through the use of genetic reporters. We looked at the ability to image vascularity and perfusion by doing dynamic contrast enhancement and looking at oxygenation. And then finally, we looked at the ability to use MSOT to image resisting cell death by using a probe specific for caspases that would allow us to image apoptosis. Our approach is, as shown today in this webinar, is in preclinical. The device we have is a proven technology with a huge interest by pharma and academia. Today's presentation has been limited mostly to cancer applications, but there really is a wide range of applications that are possible with this technology. But our interest is not just preclinical, also clinical advancement. So we've developed a couple of different handheld prototypes that can be used for different purposes. One such prototype is shown here, where we have a three-dimensional semi-sphere of detectors that are arranged in a cup-like fashion that allow us to do three-dimensional imaging of the vascularity of a human volunteer. This is done in single wavelength mode in this case, but you can see in the image on the left, we're seeing the XY plane, and we can also see the depth information on the right. When combined with the multispectral approach, which is this year been published on from the group here in Munich, you can also divide these signals then into melanin signals and oxygen saturation signals. This can be done on smaller structures as well. In this case, we show the finger, where traditionally in the case of, for example, arthritis, the vasculature of the human finger is of important note to rheumatologists, traditionally examined by MRI, but importantly, this could be done in the clinic by a physician using optoacoustic tomography. So in conclusion, MSOT is a powerful addition to the scientific imaging arsenal. It provides anatomical, functional, and molecular information in real time at high spatial resolution in deep tissue. The range of imaging applications in cancer research spans wide, and we believe that clinical translation is within reach. A lot of the work that I've shown today is supported by publications that are openly available. As Philip indicated at the beginning of the presentation, this recording will be available so you can look these publications up if you're interested. With that, I'd like to say thank you for your attention. I'll turn the floor back over to Philip to address any questions that may have arisen. Thank you.
Thanks very much, Neal. I'll actually point it right back to you, I guess, with some questions. Just to mention once more, if you have additional questions, we have collected quite a few. Please feel free to put them into the questions box on your webinar status bar, and we'll try to go through as many of them as we can. One more comment. One of the participants noticed that the references were seemingly cut off at the bottom. We'll make sure to send those references that were shown on certain slides with the webinar link, or the link to the video that we'll distribute after the webinar. A few questions came up regarding the probes. So one was, if I already work with stereo fluorescence probes in my lab, can I use those also for optoacoustics? So maybe we'll start with that.
Yes, I think that's a very good question. So as long as the absorption spectrum is within the 680 to 980 nanometer range, then these are probes that are going to work equally well in optoacoustics as they do in fluorescence. So anytime you have an absorption event, as we know, there's always an emission of photons with a higher wavelength or a lower energy. Because there's a lower energy, the remaining energy has been given off as heat after absorption of the photons, and that's when there's a fluorescence event. But according to the quantum yield, most of the time there is in fact no fluorescence, and a lot of the absorbed energy is converted directly into heat, 100%. So any probe that absorbs the near-infrared can also be used for optoacoustics.
And I think the question was maybe answered on one of the slides, but let's reiterate it again. So are you able to resolve more than one molecular probe at a time?
Yes, we can. So what we do at all times in order, since the intrinsic contrast in optoacoustic is driven by blood, both oxygenated and deoxygenated hemoglobin, those are two molecular signals that we're always measuring. In addition to those two, we can inject a molecular probe to add a third agent. That's mostly what we've done throughout the presentation, but we can also inject a second agent simultaneously, and in this case, we're looking at 4 molecules simultaneously. We haven't had the opportunity to inject 3 agents simultaneously, only because we don't have access to a lot of probes that have sufficiently different spectra. So something that's absorbing at 680 can be differentiated from something at 750, but we haven't interacted with a lot of customers that have agents that absorb, that have a peak absorbance between 800 and 900. So we just haven't had an opportunity to use more than 2 at a time. But in principle, multiplexing is something that we're always doing.
Maybe if we can jump back to slide 12 real quick. The question was, can you tell a little more about what kind of probe was used for the apoptosis analysis, apoptosis imaging, and why does the apoptosis signal overlay with the hypoxia signal?
That's a very good question. So this is something that we empirically determined, this overlay. So there's always a question when we have these. In this case, this was a 4T1 tumor that was growing and was not only apoptotic but probably necrotic as well. So this particular probe is a polycaspase probe. It's something that we market under our own name, but is also available through Thermo. And they've done all the characterization for this particular probe to show that it's specific for apoptosis. Our main goal for this experiment was to show that we could detect signals in vivo that were consistent with the biodistribution that we could document ex vivo. We also wanted to show that the signals were in some way related to apoptosis by showing an increased signal following doxorubicin treatment. So beyond that, I would probably have to refer to Thermo for more characterization on the particular probes, since they're the ones who've actually created it. But the co-localization with the hypoxic area is something that we actually see quite a bit. As to why biochemically, I actually can't say. I haven't myself investigated that particular aspect.
Maybe over to a few more technical questions. Is the equipment suitable for mice and rats?
So that's a very good question. The preclinical scanner that we have was originally designed and optimized for mice, so objects that are approximately 2 centimeters in diameter. So this is ideal for mice. It can also be used to image small rats, or particularly the head of all rats, because they have a head that's approximately 2 centimeters in diameter. The one difference that we would have to have is the holder that I showed with our animation of an MSOT experiment needs to be a bit bigger to accommodate small rats. But once a rat achieves a weight perhaps greater than 150 grams, then it's really getting too big to be imaged by this modality for the preclinical scanner, which we showed. However, as I showed at the end of the presentation, we are developing handheld probes that can be used in the context of clinical imaging, but can also be used on small animals. And in fact, some of our customers are doing this already this year, where they may be imaging mice or, rats or animals that are slightly bigger. So, for example, rats and dogs, or rabbits and dogs. So if one wants to do optoacoustic tomography with bigger animals, I would probably suggest the cup would be the best approach, the handheld scanners.
Then something about animal preparation. So the question was if animals need to be shaved before imaging.
That's a very good question. As in traditional planar fluorescence imaging, it is important to shave the mice. This is important not only because the light needs to get in without being completely scattered or blocked before it gets into the mouse, but we also have to take care that the acoustic waves that are generated are not scattered as they make their way outside of the mouse before they get to the detector. So whereas in planar fluorescence imaging, it would be common only to shave the surface facing the camera. In our case, since we take a tomographic approach, it's important to remove the hair around the entire circumference of the animal wherever you want to image. Beyond those aspects of animal handling, we have a video on our website that is a live video demonstration of the animal handling and how the animal goes into the system. The video was just too big to play in a webinar and would lag if we tried to show it. But for anyone interested in seeing how the animal handling works, I can really recommend that video.
Thank you. And a question about the timing. So the question was, how long does it take to acquire an image, or also to acquire images of a whole animal?
Sure. So an individual image, I'll first start with our laser fires at 10 hertz. If you consider a single laser pulse, then an image is generated within milliseconds. So a single image is actually acquired very fast. But the rate of our imaging is limited by how fast our laser fires. So we can acquire up to 10 images per second. If you want to acquire a multispectral image at a reasonable step size throughout the mouse, then it may take 5 minutes to do a whole body scan. But our software has a lot of flexibility with regards to how many wavelengths one wants to use and what step size one may want to use going throughout the animal, whether you want to look simply at biodistribution or do a smaller step size in the mouse to make a nicer looking three-dimensional reconstruction. In those cases, it may take a bit longer. But if you just want to look at biodistribution, it can take 5 minutes to image the mouse.
And maybe a quick follow-up question on that. The question is, do you image multi-wavelengths simultaneously?
Not simultaneously. They're one after the other, so they're sequential. If we to talk a little bit more about that, if we want to image multispectrally and look at oxygenation, we typically look at 5 different wavelengths that are imaged one after the other. Since the animal may be moving, if you want the best performance for oxygenation studies, then it works out best empirically if you acquire 1 wavelength per breathing cycle of the mouse, in which case the temporal resolution for a multispectral image would be 5 seconds.
And something on image reconstruction. How long does it take for a 3D reconstruction?
So that's also a good question. We have 2 reconstruction algorithms. One that's used during imaging to produce a live image. So this reconstruction, again, takes milliseconds so that one can always see the image as it's being acquired. This image can, in some cases, not quantify as well as one would want. So we have an offline reconstruction algorithm that takes a bit longer, that we do offline. But in principle, doing a reasonable number of images, if you want to look at a tumor or a whole mouse, it might take 10 minutes to do the reconstruction of the individual cross-sections, but then the 3D representation that can be done in our software is something that can be done almost instantaneously.
Okay. Going maybe a little bit beyond the tumor, the question was, do you have other examples beyond oncology?
Sure. I would say the most popular or the most commonly used applications that we've developed here in Munich are related to cancer, which we show quite a bit of today, neuroscience, and pharmacokinetics. So because we can image at 10 hertz, a lot of people like to see the change in concentrations of their probe or the biodistribution over time. So this is something that can be imaged very well with our modality. And then also we've developed some neuroimaging applications, which we've also published, which I think was maybe in the list of references at the end of this presentation. But the range of applications that we've developed here in Munich is not necessarily representative of the scope of what's possible with MSOT, but rather reflective of the permissions we have to work with different animal models. So our customers are actually developing our application portfolio to a greater extent than we can do on our own. But if you have particular interest in a particular application, please follow up with us, and we'd be happy to send you the information that we have.
Maybe one specific question, because it might be difficult. Experimental examples on evaluation of fibrosis, lung or liver with this instrument.
So that brings up a good point, that particular question with respect to the lung. The lung is something that is not an organ that can be imaged in any optoacoustic setup, mostly because of the change in the speed of sound in tissue with respect to air. So one cannot reconstruct the source of the signals because you must use a single speed of sound to determine the time of flight for the origin of the signal. So imaging lung fibrosis would not be possible. We've never looked at the ability to image liver fibrosis, although I think that would be very interesting to do. I think probably some of the oxygenation signals that we can see might show heterogeneities within the liver of a fibrotic mouse. We've just never had access to such a model. So this is something that we hope one of our customers will look at in 2014.
Thank you, Neal. There's a few more questions, but I think we will cut off here and then follow up with the people that had questions that haven't been answered so far individually, and make sure that, that all the questions get answered. In addition, if you have any additional need for information or questions that you want to answer, feel free to contact us anytime directly, either by email, by phone, or through the website. And we'll be happy to come back and share with you what we can in terms of information. So with that, I would like to close it and thank Neal again for the presentations, and all of you for attending, and I wish you a very good day. Thanks a lot.